So let's look at these 2-dichlorobutane. So this is similar to the 2-chloro-3-bromobutane that we were doing before, but now both of these are chlorines. And so here we have 2 enantiomers. This one's R and R, this one's S and S. They're chiral, and they're enantiomers, they're mirror images of each other. Now what we did with that other molecule is we switched the configuration at, so if we're taking this one and making it into that one, we're just switching the configuration at one carbon and leaving the other the same, and then drawing the mirror image. In that other compound, these 2 ended up being enantiomers, but here there's a plane of symmetry along the middle. So if you cut this one along the middle or folded it in half, it would match up on both sides, wouldn't it? This is ClH and CH3 and the mirror image on the other side. So that's what we call a plane of symmetry. This also has a plane of symmetry. These are not enantiomers. They're identical to each other. If we took this guy and just flipped him around, just rotated him 90 degrees, no, 180 degrees, rotated him 180 degrees, you'd get this guy. They're the same molecule. So the word we have for these is meso. These are meso compounds. A meso compound is an achiral diastereomer of a compound that has stereogenic centers. So what we did here is we're looking at all the possibilities for the configurations at these 4 stereogenic centers. Two stereogenic centers. 2 stereogenic centers, 2 to the n, 2 to 2 squared. We expect a maximum of 4 stereoisomers. Here we're drawing them out, but then we realize that these 2 are not different. They are actually the same thing. So this only has 3 stereoisomers. 2 of them, we have 1 pair of enantiomers, and then we have this one that's meso. The mirror image is actually the same as the molecule. So this one is actually achiral because its mirror image is superimposable upon itself. Some compounds do this and others do not. There has to be a plane of symmetry. Tartaric acid is one compound that has a meso form. So here's with both centers being R, and here's with both centers being S, and we look at the specific rotation. This is plus 12 and minus 12 degrees. That's what we expect. If we look at the melting points, they're identical, because melting point is an achiral property. It doesn't depend on whether the molecule's chiral or not. So enantiomers will have identical melting points. This one, we have R and S. It's got a plane of symmetry along that blue dashed line. And so it's achiral, it doesn't rotate the light at all, and its melting point is actually lower. It's 140 degrees. So show that trans 1,2-dimethylcyclopentane can exist in chiral enantiomeric forms. Well, let's draw it first. Cyclopentane. That's a ring with 5 carbons. Um, 1,2-dimethyl. So we've got, on the 1 carbon, we have a methyl group. And on the 2 carbon, we have a methyl group. And I drew one up. Sorry, didn't mean to do that. I drew one up and one down, because this says trans. They need to be on opposite sides of the ring. For a cyclic compound, that's what trans means. It's on opposite sides of the ring. It's really messy because I had my Rockstar early today, and so my hand is a little shaky. It was that or fall asleep. That's not even close. Let's try that again. Now I'm going to draw the mirror image. So here's the mirror, and we're mirroring this. So this one's on top and this one's on bottom. Are those two superimposable? So you need to visualize picking this up and trying to put it on top of this one. You can't do it. Because if you swing this around so that you match these guys up, where is this methyl group? It's going to be on this carbon, isn't it? And if you line these guys up, then this one is going to be on this carbon. They're not superimposable. Mirror images, and you can't superimpose them. These are enantiomers. This is a chiral molecule. Any questions? Is cis 1,2-dimethylcyclopentane chiral or achiral? Well, thankfully, that's very similar to the thing we just drew. Cis tells us what about those two methyl groups? They'll be on the same side. So I'm going to put them on the bottom of the ring, underneath the ring. So that is cis. And then I'm going to draw the mirror image. Now, if I pick this one up and rotate it around and get the methyl groups, can I get both methyl groups to line up? Yeah, I can. So if I rotate around this way, I can get this one to line up with that one and this one to line up with that one, and the ring will be around behind. These are superimposable mirror images. So is this chiral or achiral? It's achiral. Something that's achiral, you can take the mirror image and superimpose it. The mirror image is exactly the same. Your right and left hands are mirror images of each other, but they are not exactly the same as each other. Same thing goes with your feet and your ears. So what stereochemical term would we give this? Well, it is achiral, but that a new word we just learned. It starts with an M. Meso or meso. The mirror image is superimposable. Okay, so this is another section. I'm just going to leave it in here. This is a recap of definitions. This might be a helpful thing to keep handy. So, conformers. Conformers, you can change them into each other just by rotating around single bonds. Configurational isomers, you cannot convert them into each other by rotating. You have to break and remake bonds. So these are different substances. Then we have chiral versus achiral. A chiral molecule, the mirror image is not superimposable on itself. An achiral molecule, the molecule and the mirror image are identical. Enantiomers are mirror images. They have opposite configurations at all stereogenic centers. Diastereomers are stereoisomers, but they are not mirror images of each other. They're going to have the same configuration at least one center and differing configurations at the other centers. Any questions about the definitions?
Where does the meso come in?
Where does the meso come in? That's a great question.
Would it be an enantiomer?
It's not an enantiomer, because enantiomers are actually different compounds. The meso compounds come in when you have more than one stereogenic center. They end up being achiral. So I think it would, if you needed to put it somewhere, it would fall down here. I think they're mostly talking to you about the meso compounds because we'll run into it, but we're not interested really in categorizing things that way. Let's practice applying those terms. And there's some homework problems like this. So here's cis and trans 2-butene. If we're using Z and E notation, this would be Z because the higher priority groups are on the same side, and this would be E because the higher priority groups are on the opposite side. So are these conformers or configurational isomers? Can you convert this one into that one by rotation around a single bond? No. They're configurational isomers. Are these chiral or achiral? Well, let's draw some mirror images. If I draw the mirror image of this one, I'll try doing it up here. Then I'm going to have H here and CH3 and H and CH3. My mirror is right along here. Does that make sense? Is this superimposable on that? If I turn this around, can I lay it on top of this one? Yeah, I can. This one's achiral. How about this one? Another way you can do this is look for a plane of symmetry. There's a plane of symmetry right down the middle of this one. These are achiral.
What makes it achiral again?
The mirror image is superimposable on the original.
Were you saying that class about there being 4 different groups around the central carbon makes it chiral or achiral?
That's the stereogenic center, yeah. Is there a stereogenic center in either of these? No. There isn't. Question?
Is it fair to say then, if you have an isomer, it turns out to be chiral?
No, because chiral molecules have isomers.
Okay.
Yeah, and when we say the word isomer, that, as we've learned, encompasses a lot of
Okay.
different kinds of isomers. These are stereoisomers because they differ only in the arrangement. The connections are the same, but the arrangement in geometrical space is different. But another way to look at this is this carbon is not chiral, that one isn't chiral. There's no chiral carbons anyway, so we could do it that way too.
You said the second one is achiral because if you rotate it, it can go on top of the other one?
Mm-hmm.
I don't see that.
Okay, so if I take this and let me choose a different color here. If I rotate this around and I just rotate it, I can just keep it flat and rotate it around. Then the CH3 comes down to the bottom, and that's where this guy is. And this CH3 comes over there, and that's where this one is. So I'm just taking the whole thing and rotating it.
Even though it's a double bond?
Well, I'm just taking the whole molecule. I'm not twisting anything. I'm taking the whole molecule and just turning it around, just like with my hands. I'm just going to turn my hand around. I'm not disconnecting my fingers. I'm just turning it around.
Like backwards?
Yeah. And this one, the mirror image, is also superimposable. All you have to do is rotate it 180 degrees in space, the whole intact molecule. Are these enantiomers, this one and this one? Are they mirror images? Is this the mirror image of that one? No. Let's just refresh our memory on the definition of the diastereomers. Fine. So diastereomers are stereoisomers, but not mirror images. So I lost all my things. Fine. So we decided that one and that one. These are stereoisomers, but they're not mirror images, so they are diastereomers. They're not the same molecule, but they're not mirror images. Let's do some more examples. This is staggered ethane, and this is eclipsed ethane. Are these conformers or configurational isomers? They're conformers. Because we could make this one into that one just by rotating around this single bond, right? So those are conformers. Are these molecules chiral? Are there any chiral carbons? Are there any stereogenic centers, carbons with 4 different groups? No. So these are going to be achiral. Are they enantiomers of each other? Are they non-superimposable mirror images? No. How about diastereomers? Are they stereoisomers of each other? What does it mean for it to be a stereoisomer? Different arrangement in space, right? So these are stereoisomers. They have a different arrangement in space, but they're not mirror images of each other, so they would be called diastereomers.
And the enantiomers are
Mirror images, yes. So let's look at R and S lactic acid. Conformers or configurational isomers? Can you convert one into the other by rotation around a single bond? Well, maybe let's jump down to the second one. Are these guys chiral or achiral? Is there a stereogenic center in this one? There is. That carbon in the center there, it's got a methyl group, an H, an OH, and this guy. 4 different groups. And this is the different orientation, the different. They weren't very kind when they drew that, were they?
Looks like the hydroxyl and the hydrogen are in the same position, both of them. Someone changed to so it's
This one and this one have been switched with these two in the same position. And so that means it's the other configuration. If we look at this one, the hydrogen is in back. And so we would order these. This one is first, second, and third. That's going around to the right. This is the R. Well, actually, it just says that right there. And this is the S, right? Because here's number 1, 2, 3 going around to the left. So R and S, are they chiral or achiral? Or chiral. Right. Each of them has a stereogenic center. It's a chiral molecule. chiral molecules are not conformers. In order to switch this one into that one, you have to break this bond and move the pieces. You can't just twist them around. So that makes them configurational isomers. And are they enantiomers or diastereomers? If you have one stereogenic center, you just have two stereoisomers, and they will be enantiomers. They will be mirror images. There's only the one stereogenic center. And so this is, if we look at this as the original, this will be the mirror image. They've not drawn it to look like the mirror image, but it is. The diastereomers, if it's a chiral molecule, you're going to have two different stereogenic centers, and one will be the same and the other will be different. Meso and RR, tartaric acid. So this one has an R configuration and an R configuration around its two chiral carbons. And this one has an R and an S. I'm going to write that in. This one's R and that one's S. Are these configurational isomers or conformers? They're configurational isomers. I can't convert one into the other just by twisting. It's not going to work. You can't convert an R into an S or an S into an R just by twisting things around. You have to pull pieces off and stick them back in different orders. Are these guys chiral or achiral? Well, it turns out there's one of each. This meso compound is achiral because the mirror image is the same. It's superimposable. And so this one is achiral. That one's achiral, and this one is chiral. Is that confusing?
So what makes the other one chiral?
This one's chiral because if you draw the mirror image, you cannot superimpose it on the original. This one, because of its plane of symmetry, right here, there's this plane of symmetry right along here. When you draw the mirror image, all you have to do is rotate it 180 degrees and you have exactly the same molecule. Comparing these to each other, are they enantiomers or diastereomers? Is this the mirror image of that one? No. These are diastereomers. Any questions?